promised that I'll be taking certain topics. And yesterday I have given the names of the reference books and material. Today also I'll be sharing some handwritten notes, as well as I'll be sharing the notebook of this class. And there are certain notes on just definition type things like entropy, mutual information, etc., Krauss operator. So I'll be sharing a note detailing that, but I'm not covering those portions. So in general, it takes at least 10 to 15 class to cover all those topics. But essentially, the most conceptual part I'm covering today again. So let's start. So thank you for attending the session on Sunday. I'm very sorry. So as I have my office works and all at IBM, so I couldn't manage the weekdays. So I'm taking it on Saturday and Sunday. Okay. So the in summary, we'll be talking on density matrix. This is important, especially for the noisy quantum states, right? And the properties and all I won't discuss. Then I'll directly go to certain things on measurement, quantum measurement, specifically the projection measurement scheme and the POVM. These two part, these are important. And of course, to understand these two protocol for measurement, we have to understand um, something called the completeness relation. Okay, completeness relation. And yes, POVM. I'll talk what is POVM and also in the measurement, right? Positive operator valued measurement. Um, so if you and then I'll be talking on the most one of the most important theorem in quantum information called the no cloning theorem. So I'm sorry, yesterday I was a bit fast. Today I'll go a bit slow. And then I'll talk on the one important algorithm or protocol called the quantum teleportation. Quantum teleportation. So I'll be taking 2 hours for this. And if you allow me another 30 minutes, if you allow me, I'll show a Qiskit demonstration, Qiskit programming demo on for the teleportation circuit. Okay, how to create a teleportation circuit in Qiskit. Okay, so for this I need another at least 30 minutes. So if I see at least if some of you are there, so I can take this end part of the sessions. Okay, because that is not a theory part, that's a tutorial. Okay, so I'm trying to cover it as I mean simple way as possible. So I request those who will be doing advanced research on this topic for them to understand this topic in at least a much deeper level. We should at least go through once the real analysis and complex analysis. Um, so you can, there are plenty number of books. One of the good books is by Terence Tao. So, and this will help at least to understand various set theoretic approach to understand this part. So in general, in probability theory, we have studied. Yeah. So those who are interested to Qiskit part, please, I'll extend about 30 minutes today. I'll go till 4:30, and last 30 minutes I'll demonstrate the Qiskit, how to write a circuit, how to design a teleportation network and so on. Okay. So, but for that, we need to first cover the theory. Otherwise, it won't make sense to directly go to the programming part, because many of the participants may not know the theory. So, in probability theory, we have studied the random variable, right? And while we have studied a random variable, right? Let me take a bit random variable. So, for example, X is a random variable which basically maps an abstract space to a real number set, right? And that functional mapping, or that particular mapping, is called a random variable X, right? Which can basically takes the values from abstractions to real value, right? This mapping. Uh, and in general, when we talk about the random variable, specifically today we are talking about the discrete approach. So not the continuous variable part. So discrete variable approach, where you have the random variable which takes discrete values, right? And they have an associated probability mass functions, right? Uh, so P of X, right? So now, when you have a set of random variables, typically you can denote by a vector X vector. For example, if you have a head and tail coin toss experiment, right? And you assign these abstractions that head equals to +1 and tail equals to say 0 or -1, right? This particular set, or 0 and 1, say for example 0 and 1, tail is 0 and head is 1, right? So this abstraction plane to the real plane, that the values takes 0 and 1 from an abstraction HT, right, to a real plane 0 and 1, is done by the random variable X, and which you can also represent the random variable as a vector quantity, right, in simple notation. So we can take it as a column vector, say 1 0, like that, right? Head and tail correspondence. But in general, it can take any real value of a real value of any discrete level, not just 0 and 1. It can take any value, say for example the temperature of a day, right? Right. So, say for example, today the temperature is in India is between say 5 degrees centigrade to some 20 degrees centigrade among various regions, right? So this is the range, and it can be 5.5, 6.7, or 10.5, whatever it is. That depends on the like the sunlight and many other things, right? And accordingly, you can create this vector, and this vector can have length of n, right? So we have a correspondence X, and correspondence that X may have certain values, for example, X0, X1, X2, and so on, right, up to Xn minus 1. So I'm writing capital N, okay, capital N minus 1, and it may have a associated probability that a particular value is repeated for how many trials, right? If that is the case, that is the notion we introduce here. So we have an associated probability that P of X equals to X0, that is equals to P of 1, P of X equals to X1, the probability is P2, and so on. So Pn minus 1 is the associated probability, right? And if we draw this curve, that this is my this random variable X, and this is P of X, and X takes a particular value, little x, right? Sorry, not bar, little x, right? So X0, X1, and so on up to say N minus 1, and you have an associated probability to these cases, right? Certain probability values, that P0, P1, P2, P3, right? So on. Similarly, so now X bar, the quantum notion, when we have prepared, you have two types of uncertainty here, right? One is, of course, the how you represented your information. Say ket psi, it's also a column vector, right? And for a two or a single qubit case, 1 qubit representation of the information that we have seen is alpha ket 0 plus beta ket 1, right? So in the hardware notion, what does it mean? And in mathematical notion, what does it mean? Right. So it's simply a just a vector representation in two bases, right? In mathematical, it's a vector representation of a state, of a quantum state into mathematical basis, and the basis are 0 and 1. That's all, right? And typically it can be a vector like this. If this is 0, this is 1 to orthonormal basis, and this is my quantum state. This is the amount alpha, this is the amount beta, right? That's all about this. But in hardware, suppose I somehow I can measure a particle, right? And I have to say whether it is in the plus pin or it is in the minus pin, right, at a particular moment. Okay, so when you do the measurement, if you can measure it, right? Or example, suppose there is an energy level of a particle and it has a probability distribution like this. So at a particular moment you measure and you see whether you can see it in the ground state or fast excited state. So ket 0 and ket 1. So in different way, how you do measurement using the pulse, microwave pulses and all in the superconducting setting, or in the spin qubit, there are other various measurement scheme to understand various spin structure of the particular quantum phenomenon, right? So whatever it is, I can, in general, mathematically, I can always write it as a vector, and my component are alpha and beta, right? And because it's a it's coming from the quantum mechanical phenomena, this particular. So there is randomness in alpha and there is randomness in beta. So this is the first level of uncertainty, right? First level of uncertainty. So first level of uncertainty of what? Of what? Of the particular quantum state, either it is in state 0 or it is in state 1. So this is the first level of the quantum state, either in state 0 or in state 1. I was just presenting as a superposition of that, just simply a vector representation. But if I do measurement, I can get some value. Okay, it is in the state 0 or it is in the state 1, right? Now, this is the first level of thing. So we know that there is certain randomness. Now, another level of randomness is I create this particular state, right? I generate it with certain um, physical hardware, right? And I have a desired alpha and desired beta, right? But every time I prepare this state for experiment, I need to repeatedly create this state, right? So I get that the realization of psi is not psi. In fact, every time I generate a psi, say psi 1, psi 2, certain realizations, say psi n, right? And they may not be the same value. They may not occurring with the same alpha and beta, right? So we call this as ensemble realization, ensembles of quantum states, right? And they can also have certain associated probabilities like P1, say P2, and P, if it is N, so it is Pn, right? So a number of realizations it can have. These are the associated probabilities of these states. Yes, ensemble. Yes, ensemble means you can think sampling of a quantum states at multiple time, right? But it is not the exact sampling. Instead, you are generating the state multiple times, right? So in mathematical sense is that you don't have psi, which is called a pure state, but you can recreate the states multiple times for whatever applications it is. You may not always get the same state again and again, right? So you can have a set of very similar kind of the states, say psi1, psi2, psi3 at different time instant, for example, right? And you call this set, the set of collection of all those realizations, as ensembles of quantum states. Okay. Um, so a better way of calling the ensemble for noisy states, whether you will call this is a noisy or not, that's a different debate. But in general, if you have realizations, multiple realizations of the same state, so we have an say quantum state, in state I write as psi x, right? And associated probability p of x, right? This is the case. And this particular set that I have a state and I have an associated probability, these combinations, this combined set for this little x belongs to say some capital X, where capital X is the random variable of collections of all the states. And this collection is called the ensemble description. This is a more concrete definition of ensemble. Okay, so you have you have certain random variable x and associated probability mass functions p of x, right? So you have an x comma p of x, right? This is a classical ensemble, and this is a quantum ensemble, right? You have a quantum state and you have an associated probability mass functions or the PMF for those particular discrete states. Okay? And to understand this concept in a better way, how to understand this set of ensembles, can you describe quantum states? Quantum states, which the states may not be pure. How to represent quantum states in a better way? That combines this uncertainty that it has a probability mass functions. And the approach is called the density matrix approach. So in the density matrix approach, the definition is, okay, density matrix can be represented by rho, sigma, pi. These are various notations in various books. Okay, so in general, rho is defined as sum of pi psi I outer product of psi I. So instead of representing a quantum state as a vector, oops, so can we represent as a matrix or operator? Right? This is the question. So earlier we are representing quantum state by column vector ket psi, and now we are representing as rho, right? Now if you have a so this is also very similar to the concept that is we call the expectation value for a random variable of a classical random variable, right? So what we do, we have an associated PMF, P of x and the variable x, and take over sum for all such little x, right? So this is the value we called as expectation value, right? In classical. In quantum, you have an instead of this x, you have something that is the quantum state psi, right? And instead of psi, you are taking an outer product of psi and psi. So you are eventually creating a matrix, right? So for example, suppose let's take some example to understand this better. So suppose I have a fixed state ket 0, right? And suppose ket psi is ket 0. This pen is always creating a problem. So sorry for this. Right. So if you have the state 0 and the 0 is basically 1, 0 is the quantum state, you are taking the basis state itself is a quantum state, that my quantum state on the Bloch sphere is here, right? This is my K0 state, right? Then what is the density matrix? 0 and 0 outer product, right? This is my density matrix, which is basically 1, 0 times 0, 1, right? 1, 0 this way. So you will be getting a column vector times the row vector, which is basically equals to 1, 0, 0, and 0. So this is the density matrix representation of this north pole, or the basis vector K0 itself. Okay. Yeah. So of course, this looks like an projector operator, but there is an associated this pi probability, right? So we'll come to the projector operator part in measurement POVM. Okay, we'll come to that point. But for the time being, just let's stay. So Ket1 has an equivalent density matrix representation of Ket1 outer product Ket1, which is equals to 0, 0, 0, and 1, right? Similarly, this plus state, right? Plus state we have seen how to create plus state. If you have a 0 state, if you apply the Hadamard gate, you are getting the state, right? Yesterday we have seen. So plus state is defined as 1 upon a square root 2, 1, 1, right? This is our plus state. And the density matrix for plus state equals to plus state outer product, which is 1, 1, 1, 1 by 1 by square root 2, right? So this is the outer product of the plastered representation. Sorry, this is not square root 2, this will be half, okay? Square root 2 times square root 2, it will be 1 by 2, okay? And this looks like Hadamard matrix, but it is not Hadamard matrix, okay? So similarly, so in general, if you have a fixed state, like I know the exact value that, say for example, a quantum state psi is alpha Ket0 plus beta Ket1, right? And of course, if I am very sure beta Ket1, so the outer product of this, what will be the value? So alpha 0 plus beta 1. So you have to do the outer product alpha 0 and beta 1 outer product, right? So you can calculate, it will be a matrix, something like this, alpha square, beta square, and beta, beta alpha and beta star. So you just calculate this, check this value. Most likely one of them will be beta alpha star and another will be something alpha beta star, something like that. Okay, if alpha and beta are complex number. Okay. So then we can see if there is 100% certainty that earlier I was taking either 0 or 1. So this alpha beta has no uncertainty, right? So that's why this matrix, if they don't have uncertainty, so your that every time I measure 0, I'll be getting 0, right? If this is the scenario, that particular case means you have an uniform distribution of Ket0, right? Uniform probability distribution, then this row will be defined as only psi and psi outer product, because as many realization you take, right, you have the same outcome, right? On an average, you'll be getting this outer product psi and psi, right? So this is also called the density matrix for pure state. Pure state. But in general, due to hardware impairments and communication effect of communication channel and all, or how you are preparing the state itself, these alpha beta coefficients can basically vary a bit, and then basically the general definition will be this one, right? This is for any quantum state, right? Now, okay, for clean definitions, you can always remember this one. So, I mean, just instead of this X business, we can also write in terms of I as P of I, ith index of realization, psi I and psi I outer product. Okay, where I is the number of realizations that you are doing. Okay, now some important relations. One is the trace. So trace of an operator A can be written as sum over all realizations I, expectation of like the IAI, this inner product. Okay, where I this particular set, like the ket 0, ket 1, ket 2, and so on. So is some complete orthonormal basis set. Okay, complete orthonormal basis for this operator A. Okay, so this is just a definition of trace. Those who have difficulty to understand this exact definition, so please go through the either in Chuang or in Wild book. Okay, the detail is there. So this is just the relation, an important relation of a trace. So of course, trace is the like diagonal sum element, right? So sum of the diagonal element of the matrix, but that is also equals to this one. Okay, when specifically you have an operator and that you represent a quantum state in certain orthonormal basis of that particular operator. Okay. And also, I think I have also covered it in QT-23 partly at least. Then there is something called the expectation. Expectation of the density operator, that is called the expected density operator. So this is same. I mean, by the definition also, this is also you can write as the expectation of the outer product of the psi x and psi x. So instead of the in case of the random variable, I was saying if x is a random variable times the probability mass functions, right? And if you take the sum, right? So xi and pxi, right? This is the case. So you get the expected outcome, right? Or the expectation value of the random variable, right? So in this particular case, instead of xi, so this is just like this is same as the expectation of your the random variable x, right? If you write this way, right? And this is same as this one, expectation of the outer product of the psi x and psi x. So every time you get this matrix, right? So what is the expectation of this matrix over various realizations, right? So that is the density matrix, and this is this definition and this definition is the same. Okay, just a different way that we can write. Now there is one or two important property I'll cover and I'll stop it. So one is the spectral decomposition. Okay, there are some more properties. Okay, I'm just not covering. These are your homework. Like for example, this rho is a positive semi-definite matrix. We have to either you can prove it. Second is rho square is called the purity. Okay, it is always greater than equals to 0, right? And there are some other properties like the trace of rho is always equals to 1. So because the probability sum equals to 1 and so on. So for the pure state. So these are various properties of rho is there. So you can just go through from textbook, or I'll be sharing the notes for that. One important property of rho is that because rho is a positive semi-definite matrix, so we can represent rho in terms of the eigenvalues and eigenvectors. So rho x phi x outer product phi x, where over x equals to say 0 to some d minus 1 if d is the dimension of the matrix. So every density matrix rho has a spectral decomposition in the eigenstates, where this rho is a Hermitian matrix. In fact, by property, it is positive semi-definite matrix. By positive semi-definite, I means if there is a vector x, then x star rho x, this particular value will be greater or equals to 0. Okay. So this is called, then rho is called the PSD matrix. Okay, positive semi-definite. Semi-definite matrix. Okay. For example, if you have a quantum state psi, and if rho is the density matrix, then psi star rho psi, you can write it in the Ket notation. So it will be, so better to write this way. So this way, this quantity will be greater or equals to 0. Okay. So this is just a simple notation, just algebraic notation, and this is the Dirac notation. Okay. Dirac notation of the same thing. So where lambda x is the eigenvalue, and corresponding vector phi x is the eigenvector. Now you can ask me why this is certainly important, this eigenvalue decomposition. So we'll see this in POVM measurement. This is extremely important. Okay. So now a question may come like this: a maximally mixed state is given by. So suppose a question I'm asking: a maximally mixed state is given by. Suppose pi is a density matrix. So which one of this is a maximally mixed state? 1 by d. If d is the dimension of this matrix pi, d cross d, then 1 by d I outer product. I is the orthonormal basis for the matrix pi. Option B is, suppose this is option A. Option B is identity matrix. Option C is identity matrix of dimension d cross d, for example. Then pi equals to I by d. And the last option is all of this. So can someone answer in the chat box? Of course, when we suppose we transmit a data x, right? And the bit string in the classical transmitted data is the set 0 and 1, right? But when it will be maximally mixed state, if you get the probability of 0 and 1 at the receiver end y as half and half, right? Then we call this as a maximally mixed state of 0 and 1, right? So which of this particular case is a maximally mixed state for the density matrix? There are 4 options. Any answer? Okay, just write the option. Some there are some answers who are saying A is correct. Okay. Anything else? Option B is wrong. This is not the correct answer because the identity matrix is all 1. So this is not a normalized state at all. Okay. So this is in fact not a valid quantum state for the density matrix representation, right? Yes, this is also correct. So option A and C are correct. B is wrong, hence D is wrong, right? Okay. So now let's talk a bit on the noiseless evolution, and then we'll come to the noise evolution. So we have seen this noiseless evolution yesterday, but just formalizations of that. So we have a quantum state psi a psi, for example, psi x, right? And x can vary, right? Or psi I you can write like that. And it has a quantum, it passing through a ideal quantum circuit. Okay. And what you are getting is quantum, say, psi y. This is you are getting at the receiver, right? Or at the end of the evolved quantum state, right? This is the scenario. So of course, this you can write as u psi of x, right? So now if it is a set of ensembles are there that you have certain uncertainty in preparing the state kit psi, right? So when you are preparing the state kit psi repeatedly, right, for regions or repeating the experiment, and you have an ensemble description of the problem, so then of course you have a density matrix rho x, right? And which has which you can define from the ensemble description of that. So that is the rho x of x and u of these okay, so rho x of x and this psi x, right? This is the ensemble description at the input side, right? Here. Now you have an ensemble description here. Because there is uncertainty here, so that uncertainty propagate here. But the good part is that u is fixed, right? There is no uncertainty in the channel. Channel part is fine, right? So what is channel? Channel is just a mathematical functions, right? And that function basically simply uh, so a classical channel, suppose for example x, right? What it does, it basically maps the input symbols to the output symbol, right? This is a classical communication channel. And a particular quantum channel is, or the channel here in our term is another set of functions, or a unitary matrix, you can say u, right, which convert the density matrix rho x to the output density matrix rho y. So it's just a functional mapping from input density matrix to the output density matrix. That's what we call a channel. An ideal channel u has no noise. For a noisy channel, you can have a interactions with the environment, or the so there is something called the system and the environment, or bath and environment. So that interaction is there. Suppose this environment itself can interact with the environment, right? So that particular case, so suppose for example environment has a Hamiltonian unitary or non-unitary evolution it can have. So if it has certain evolution, noisy evolution UE, and your system has certain evolution US, that means your quantum gates that you are applying, it is noisy, right? That particular case, it will behave as US tensor product of UE in this form, right? This is itself the system and environment can together form a composite quantum system. And this rho x will experience this another level of uncertainty here. So input, there is certain uncertainty and passes through a channel, and that channel itself is noisy. And then you can have a outcome state, or the evolved state, right, at the receiver side. And that can, of course, it will be another level of like uncertainty, right? So you have uncertainty in all the three cases, it can appear, right? So for the time being, so how to treat this part? So there are how it is interacting with the environment. So there are like topics, specifically various cases of noisy channel, such as the depolarization channel, bit flip channel, phase flip channel, various I mean types of quantum channel are there, how we model the informations. And we can represent this kind of channel with a particular set of mathematical protocols, which we call the CPTP map, complete CPTP map, complete the trace preserving operator. Also, one of the special case of CPTP is the Krauss operator for formulation. So I am not going to this direction because it will take another at least 4 or 5 classes to understand this part, but I'll be sharing some of the notes to these directions who are interested. Okay. because of lack of time. So now suppose the case is that we have a rho x here, right? Because we have psi x, right? And it passes through u, and we have certain psi y, right? So the rho evolved will be because the ensemble here will be the probability distribution x will be following, because I'm not assuming there will be additional uncertainty. The uncertainty that is there in x, it is only propagating to y, right? And hence the probability mass function intact for this case, and you have only an evolution of the quantum state u of psi x. This is the things additionally it is coming because of the quantum evolution of the state psi x, right? And x is here the random variable. So this is a small x and this is a capital X. Okay. So what will be the evolved state? Evolved state will be the expectation. That is the px of x and outer product of this part. So which is u of psi x, right? And psi x of u dagger, right? This is the part. So what I have done, I have written this form directly here, and star of this part. That means this part will come here as a column vector, will become the row vector, and this u will become u star here or u dagger here, right? So the same thing, star or dagger, whatever you wish to write, you can write. So then immediately this part is row, right? So you can write it as u of, because u is free of x, right? There is no uncertainty in u, so you will become you will go outside. So it will this sum you can take inside, and u is this independent of the variable x, so u is going outside. So sum of px of x, psi x, psi x, and u dagger outside. So this particular quantity is rho x, right? So this is u rho x u dagger. So this is the rho evolved state or the outcome state, right? So with this, so of course you can understand, okay, if this u is basically a composite quantum state, I mean it's interacting with the environment. Of course, this thing will change, right? And the equations will also change in various cases, right? Now let's talk a bit on the completeness relation. Then we'll go a bit on the measurement, and we'll go directly to the teleportation framework. So just we have seen that the density matrix of ket 0 is 0, 0, right? Because there is no alpha part. Alpha is 1, right? And beta is 0 for this particular state 0. And density matrix of this ket 1 is 1, 1, right? This is the case. Now let's add these two part, right? Suppose this 0, 0 and 1, 1. Let's add these two quantity. So just adding this two part. So this is 1, 0, 1, 0 plus 0, 1 and 0, 1. Just matrix multiplications, right? Vector like just outer product of vectors or matrix multiplications, whatever you say. So this is just, we have seen this one, this plus this 0, 0, this 1 all rest are 0 and all 0 1, right? So this is simply the 1, 0, 0, 1 or the identity matrix, right? In fact, we have also seen for the state plus, right? You can also check that plus state plus minus state, this is also equals to 1, right? So if you have a quantum state, particularly you can create this kind of thing. And just a few seconds ago, one of the participants was telling about the projector, right? So this is the projector part. So individual, you can create a projector operator uh, given a particular quantum state. Say you have a vector, say u and v are two orthonormal, if they are the orthonormal bases, right? For the matrix A, then you can create this kind of projector operator for them, u and u, and v of v. If they are the complete orthonormal basis, then this will add up to identity, right? And this particular relation is known as whether it is 0, 0, 1, 1, plus, plus, minus, minus, altogether, this particular picture is known as the completeness relationship. Okay. Additionally, we need to know certain other things. Okay, so yesterday we were talking about the eigenbasis of the operator x and g, right? The phase flip operator and the bit flip operator, right? So that particular concept will be again reused today, right? So G operator is very important. So specifically, oh God. So yesterday we have seen, if we take the G operator, this is we typically use the G operator as a measurement operator in Qiskit. Um, or any other, most of the quantum simulator or quantum computer, you will see that G operator is used for measurement, right? And why we use the G measurement? So yesterday we have seen that because we represent in general our information, in computational basis, right? Computational basis set. And by computational basis, I mean Ket0, Ket1, or for multiple qubit 0011 and so on, right? These are known as the computational basis set because we are computer understand 0 and 1, right? So that's why we call this orthonormal basis set as computational basis set, right? And an important property of G operator is that G, when we apply to Ket0, we get Ket0 back. When we apply to Ket1, we get minus of Ket1. So that means this equation is following Ax equals to lambda x equation, right? Eigenvalue equation. And lambda equals to +1 for this particular case, and lambda equals to -1 for this particular case, right? So these are the eigenvalues, and computational basis itself are the eigenbasis for G operator. And this is extremely important, right? Because eigenbasis is required where you what quantum physics says. Quantum physics says, specifically the quantum postulate, quantum mechanics postulate number 2, it is saying that every physical quantity psi, they have an associated operator, say h, right? Operator h, and when you apply this h operator on that particular quantity psi, right, you get a eigenvalue of that particular operator as your measured outcome, right? And that particular, this is particularly second quantum postulate of quantum mechanics. It's basically the eigenvalue equations where the eigenvalue is the measured quantity. For example, this is the energy quantity, right? And this is the Hamiltonian operator. Hamiltonian operator. So what is energy? Energy is the eigenvalue of the Hamiltonian operator, right? This is exactly what it is telling. So we have to, if we want to find a measurable quantity, that should be the eigenvalue of a Hermitian operator, right? Which is Hamiltonian here, or the Hamiltonian operator here. So we have to choose a particular quantum gate, because quantum gate is basically an operator, right? Mathematically, it's an operator or a matrix, right? Whose eigenvalue will give me the measured value. But I am representing my informations in the computational basis. If I measure in any other basis set, right? So that case, I have to prepare all those eigenbases for the measurement. But
I have a ready-made basis set, which can I use that ready-made basis set, that is the computational basis set, as eigenbasis? The answer is yes for the G operator. Okay, that's why G operator is extremely important. And we can also represent this G operator as 0, 0 outer product minus 1, 1 outer product. For completeness, this is plus, but for G operator, this is minus, because G operator is 1, 0, 0, minus 1. And you can check this one just simply by doing the math. Where this 0, 0 is called the pi 0 operator, projector pi 0 is 0, 0, and pi 1 is 1, 1, right? So these are the projector operator. And minus of the projector operator represent the G operator, right? So when you apply this G operator on the bit string, the bit string in the state quantum psi, you get the eigenvalues, and how many times that eigenvalue plus 1 is repeated or minus 1 is repeated, depending on that, you can count the probability, right? So that is why this G operator is extremely important. Okay, so why it is important? Because so if you, for example, you have a quantum state psi, right? And if you apply the projector pi 0, right, and take the expectation, right? So it will be psi 0, 0 psi outer product. This inner product is psi 0 and 0 psi. Then you are getting alpha star alpha, that is equal to alpha alpha square. This is the probability of getting the quantum state psi in the computational basis 0. That's why this psi 0 is important, right? Similarly, psi I1 psi will give you the probability beta square. That means the quantum state you are getting in the computational basis 1, right? Now you repeat the experiment for n times and see how many times you are getting 0 and how many times you are getting 1. So that then basically the probability of 0 will be P1, which is getting the number of times get 0 out of n experiment. P2 is the probability of getting the number of the computational basis 1 out of the experiment n, right? So then you can plot that, okay, this is my ket 0 and this is my ket 1, and it is having the probability P1, it is having the probability P2, right? And this is called the histogram of the quantum information represented in the computational basis 0 and 1, right? So this is the typical plot we will see now on the Qiskit. So I'll give a demo just at about say 5 p.m. So just I'll take the some more things and then I'll come back. Okay, and there are some more theories. Just for the time, I'm skipping some of them. Just allow me. So I'm just giving 5 minutes break and we'll come back. And if you have any question, please feel free to write it in the chat box. Those who wish to write code with me, they can at least within an hour, please make your laptop available. And we'll write the code in VS Code, but anyway, you can write it in Colab or any other Python environment. For that, you need to install the Qiskit. Okay, pip install Qiskit. You can do it a priori, and we'll see it around 5 p.m. I mean, any Python environment you can download, or if you have internet, you can do Colab also, for example. This is also fine. This is also fine without download. You can, if you have a Google account, you can just open the collab I just posted in chat from the using your Google Drive, and you can do pip install Qiskit. I have just written. We'll start at 3.5. The detailed installation guide is here. You can see the detailed installation guide. But at least you need these 2, 3 comments. I'm giving additional resource for those who are very new to Qiskit. They can also look at this particular link, Hello World program in Qiskit. So you can, I have given multiple links. You can copy and save in your desktop. Sometimes when you get time, you can look at. So we have a detailed guide on this Qiskit programming for real problem. So that's why we approached this book. I'm not just doing publicity, but just for reference. I have some copies. I shared about 100 copies to some of the professors. So and the price of this book is kept like very less, just for the publishers page price. And this book is good. You can right, Devanshu, thank you. So Dr. Devanshu has retained the guidelines. You can, yeah. And the links that I have provided, all the IBM links, please, you can use those links. So there are also detailed installations guides are there. So let's start maybe. And there are many things to cover in quantum information theory. I'm just skipping many important things also. The conceptual portions I'm trying to cover, and now we will directly go to something called the no cloning theorem. Okay, let's take another one maybe. No cloning theorem. So in this particular topic, yeah, thank you, Dr. Devanshu. So yeah, I mean, this is based on only the QT series that we have done with MNIT, and there were huge requests because we did not think to write this book because there are already very good resources on quantum computing, especially the Professor Chuang book, Mark J. Wild book, and many other very good books, especially the John Peirce Skills lecture series. So all these are extraordinary material. So then we got a huge request from like the audience, especially from the MNIT, this lecture series, that can we have an industrial best books, simple things. So we tried to articulate those details in this particular book, and we tried to write it in a way that anyone, anyone from any background who are interested in quantum computing and has only class 10 level mathematics knowledge, so they can start like that. Yeah, thank you. So, so in no cloning theorem, what is the statement of the no cloning theorem? And then we'll give a rigorous mathematical proof. So, the statement is that it states that it is impossible. It is impossible to build a copier device. Well, the note that I'll be sharing today, the note that I prepared using various internet resources, right? Books, resources, as a LaTeX PDF document that I'll be sharing to Pillai sir, and you'll be getting those notes. So the proof of the no cloning theorem is a bit different there in the note, but the way I am doing the proof of the no cloning theorem here is a very simple way of proving the theorem. So it states that it is impossible to build a copier device that could copy any arbitrary quantum state, right? So what does it mean, right? So so suppose you have a classical memory, right? And in classical memory, what are the things we have? We have like address, right? And we have in a particular memory address. Suppose this cluster of memory is A, and you have classical information, say C1, C2, and C3, right? And these C1, C2, C3 are the values, right? These are the two things, right? So in engineering, probably 10, 15 years ago when I was studying, and it was part of the syllabus that we were writing the values as A in C programming, and it was the probably ampersand A, the address, most likely. I may be wrong. So something like that. So you have two things, right? But in classical, you could copy these things, information of C1, C2, and C3. Suppose you want to copy the first information C1, and you want to store the particularly in the memory register, classical memory register, or RAM, random access memory, or wherever, whatever you call, that you want to copy C1 from register A to register B. That is something operation that we call copy, right? And we have written programs for that, right, in C and all for the classical thing. And suppose you have now a quantum register, and you define a quantum state, say psi, right? And in a suppose there is a fictitious some memory, that kind of thing that we call the quantum RAM, quantum random access memory, suppose, right? Cluster of quantum memory, where you want to copy from the cluster A to cluster B, such that you have the information in A and you have the information psi after the copy. And whatever copy you do any operations in quantum, we define by U, right? That's a unitary operations, right? So copy, that the word copy has a mathematical sense, right? So what we were doing in classical things, suppose you have a data in A, you stored in C, and then C you stored in basically B you stored as C, right? Or directly, I mean, that's how we have done. So some part of the A you have stored somewhere, and then from C to you have copied to B, or directly, if possible, you can just copy the A to B. For example, B equals to A. That's how we have done, right? By using third variable or without third variable, whatever it is, right? And in quantum, you have an unitary operator U, such that the purpose of U is basically copy information from memory cluster A and paste it in B, right? And no cloning theorem says that it is never possible, that you cannot copy quantum information. Never possible. Copy is never possible, right? So let's prove this. And right. And we will prove this particular phenomena by contradiction. Prove by contradiction. So suppose there exists an unitary matrix U, or a quantum operation U. Suppose there exists a quantum operation U, which is an universal copier, and suppose we have an input state. Why it's coming? We have an input state that is the state psi, which is alpha kate 0 plus beta kate 1. Suppose this is my quantum state in very simple way. And let it be in first qubit, for example. So suppose you have a circuit, right? And uh, and and uh, and you want to, suppose you have a register A and you have a register B, and A has the quantum information psi, right? and somehow you have done something, some quantum this. Okay, let me draw the circuit here. Suppose you have a quantum cluster register A and cluster of quantum register B, and A has quantum information, say psi, and somehow you there is an operator U such that this state is also psi and this state is also psi. This is the scenario. Suppose, and this psi, suppose let it be in the first qubit, right? And let's there is an auxiliary qubit. Suppose this auxiliary qubit is B, for example, right? And there is an let let's take an auxiliary qubit which is in the state gate 0 as a second qubit, as a second qubit. Right? And purpose is what? The purpose is that the purpose of the mathematical operator U acting on the joint state. This is the joint state. This is psi 0, right? The joint state is psi and 0 tensor product, right? And it should give the output psi and psi, right? That is what we are expecting. This is in the register A and this is in the register B, right? So we have to understand the mathematical construction first. Solution is fine. Solution is everywhere. But the problem we have to understand very clearly. So no cloning theorem means if there is a cloning theorem, that means we have a quantum operation exist, that is U, that is acting on the first register, and there is a vacant second register, such that in the both the register I have the same quantum information psi. That means this state means so I'm writing it here, alpha gate 0 plus beta gate 1 times alpha gate 0 plus beta gate 1. So let's expand this part. What are the values? Alpha square 0 0 plus alpha beta 0 1 plus alpha beta 1 0 plus beta square 1 1. Suppose this is my equation number 1. Define not clear. If you have, sir, if you have any question, you can post maybe. Um, is it not visible, or the way I am presenting is not the right way? Okay, defining the copy part. I see. Okay, let me explain again. What is copy? Copy means you have two registers. To suppose equivalent classically, you have a memory A and you have a memory B. This is a quantum register. Quantum register. We have register means we studied register like transistor and all. So we have a quantum. Suppose we have a quantum register A and quantum register B. A has the information psi. You know certain quantum copier device, universal quantum copier device, such that B, which started with 0, now has the state psi, and A also has the state psi because it is copying. That means A and B intact, they have the same informations, right? This is just a same thing. A registers has the data and B register has the data, the same data, right? So that means you applied U, and this mathematically this part is what? Tensor product of psi and 0, tensor product of psi and 0. I omitted this notation here. Okay, this is not required. So U psi 0 will become psi A psi B. That means both have the same information. A registers and B registers has the same information psi, right? This is by definition, right? Yeah, this one, and then this one, right? Just I express this psi as alpha 0 beta 1 alpha 0 beta 1, right? Now um at psi is Psi is any arbitrary state. I mean, arbitrary state. What do I mean by arbitrary? Means I haven't specified the value of alpha beta. They can be any value, any complex scalar quantity, right? They can belongs to any complex quantity C, complex scalar quantity C, right? And because it's an arbitrary, then ket psi can have value, or it can be ket 0 and ket 1 as well. I mean, one of them can be 0, alpha can be 0, beta can be 0, those are probable values, right? Then that particular case, U00 will be 0, 0. I'm just making the psi equals to 0, ket psi equals to 0. This is a possible state because beta I can take 0, right? And also U10 will become U11, right? Because I'm copying this information here to here, so 1 and 1, and that is the purpose of U, right? So then, if that is a possible case, then U of alpha ket 0 plus beta ket 1 times 0, this is now psi, right? Any generic psi with alpha 0, alpha and beta, they are not equals to 0 in this particular case, right? Then it will become alpha 0, 0 plus beta 1, 1. Just this part is from I'm taking from here, right? So this is a general case, but for this particular two special case, where U00 is alpha 0, 0, and U basically 10, that will be beta 11, right? By from here. So this is suppose equation number 2, right? So now if you look at equation 1 and equation 2, right? So this part is fine, suppose, and this part is suppose it is fine. But in general, these two quantities we still have, right? Alpha beta 0, 1 and alpha beta 1, 0, right? So this 1 and 2 basically, 1 contradicts 2 because we can always have certain alpha and beta. There should exist some alpha and beta such that alpha square 0, 0 plus alpha beta 0, 1 plus alpha beta 1, 0 plus beta square 1, 1 may not be equals to alpha 0, 0 plus beta 1, 1, right? So hence the linearity of quantum theory contradicts here. That means there doesn't exist any as such U, right? So uh, that means we do not have an universal copier machine such that we can operate this psi 0 state to psi state is not possible. That means the information from A register to B registers cannot be copied. That means there doesn't exist any such U, right? So this is the proof of the no cloning theorem. Now let me take a case. The case is suppose suppose alpha equals to 1 and beta equals to 0, right? Or alpha equals to 0 and beta equals to 1. This is the only exception, right? if alpha equals to 1, beta equals to 0, or alpha equals to 0 and beta equals to 1, then 1 equals to 2. Equation 1 and 2, you can check they are same, right? So that means we can copy, right? Um, but when we say that psi equals to of course 0 or psi equals to of course 1, that I have definite understanding of the quantum state in 0 and the definite understanding of the quantum state is 1, that means we do not have anything quantumness. Quantumness is vanished, right? Because I have definite understanding of the quantum state in 0 or quantum state in 1, right? And that is what this particular exception is saying. And that's what that particular set of information is called the classical states of information. With whatever probability you associate, either with 0 or with 1, because superposition is lost. So then your quantum information becomes classical information. Hence, classical information is a subset of quantum information that we can see from the this particular no cloning theorem as a exceptional case. Okay, so that means you have prepared the this kind of state, that is fine, but they have definite presence. There is no uncertainty of 0 and 1. There is no superposition of 0 and 1, and hence this is a definite state and this is classical. Okay. So it has several applications, right? So especially it underlies the quantum security, quantum key distribution, QKD protocol, that attackers cannot copy that. Attackers cannot copy quantum states, right? That two parties used to establish the secret key, and that is the fundamental of quantum security. And another just following this this quantum no cloning theorem, and we'll be designing a protocol that I cannot copy, but how can I transfer the quantum information from A to B? Suppose I cannot copy A to B, but how can I transfer this information from A to B? Right. Right. Of course, when you transfer A to B, then the state of A is lost, right, by theorem. And this particular phenomena is called the quantum teleportation. And I'm giving a 2-3 minutes break, and we'll come back with the theory of quantum teleportation, as well as I'll show a Qiski demo on this. Okay. So taking a 2-3 minutes break, and we'll come back at 4:30. How is there there is a question, is there an explanation of the same kind for how the quantum state are reversible? Quantum states are not reversible, quantum operations are reversible. Okay. You can prove it just taking this question. any quantum operation. Say for example, the not operation in quantum. So all gates are reversible. So x is what? X is your 0, 1, 1, 0. What is the purpose of x? Purpose of x is that if you have a quantum information 0, and if you apply a quantum gate x, Pauli x gate, you will be getting 1. That is the purpose, right? And if you apply this gate twice, that means whatever information you got, just apply another x gate here, right? So that means if you apply twice of these operations, x and x, or x star x, say in this way, so you have 0, 1, 1, 0 times 0, 1, 1, 0. And if you just multiply, you'll see this is 1, 1, 0, 0 identity matrix. That means all these matrices, all these quantum operations are unitary matrices, in fact, right? So U star equals to identity matrix. That's why all the quantum operations are the reversible logic operations, right? But this is not valid for classical operations. I mean, some of the classical gates are reversible, but not all. Not that Pauli matrix. It can be any Clifford or non-Clifford gate. It can be any valid quantum operations. As soon as you take the isolated quantum system case, right? But there is complicated physics. I'm avoiding those part, especially for the non-unitary dynamics, the open quantum dynamics. Some of the topics I work with Riken directly with the quantum information physics theory lab in Japan. And for those cases, there are exceptions that you can have operations which may not be unitary, but this is outside syllabus. Am I not audible? Can someone confirm? There is one point. I'm audible, right?
Clearly audible, sir.
Yeah. So those who are facing problem, sir or ma'am, kindly rejoin. Then you can. Yeah. Okay. So let's start the teleportation theorem, and okay, let's take another notebook. Quantum teleportation. This is very important protocol, and we'll see the demonstrations also. So first, let me demonstrate the theory, and then we'll come back. So in quantum information theory, entanglement is treated as a resource. Okay, if you ask me to define entanglement from like a question to physicist, I am illiterate on this. Okay, I don't have a good definition of entanglement, but as a mathematician or a mathematics student, it is a correlation, strong correlation. Okay, and the strong correlation of at least two bodies. Okay, two subsystems. And yesterday we have seen this is denoted at least with the Bell state kind of preparations. We have denoted as 5 plus state, right? So that is a unique property, and that is a composite state. Also, we called as an entangled state, and which although it's a state of multiple system, but you cannot decompose into individual product states that we have seen yesterday, right? So we call the state. mm, we call the state this 5 plus state, that is yesterday we have defined, and we have also drawn the circuit for this, right? This 1 by square root 2 0 0 plus 1 by square root 2 1 1, right? Right. So then this we call this particular state as representing one unit of entanglement. One unit of entanglement, also called an E-bit. So this is called an E-bit, okay, entangled bit or E-bit. So we'll also define, okay, this circuit also we have drawn, right? How to do this circuit. So there is an Hadamard gate, right? And there is a C0 gate. This is the C0, right? And if you start with 0 0 here and here, so you'll be getting here as 1 by square root 2 0 0 plus 1 1. So this is the circuit we have prepared yesterday, right? Yeah. So now certain terminologies that we will be using for the teleportation protocol. So please keep patience because I'll be writing certain things for the sake of understanding. So we say that Alice and Bob share an EBIT. We say that Alice and Bob share an EBIT means Alice has a qubit or a key or a quantum information that is stored in the register A, or in simply we say Alice has a qubit A, Bob has a qubit. Alice and Bob are two persons. Alice has a qubit A and Bob has a qubit B, suppose. And together, the pair A and B is in state phi plus. They share an E-bit, right? They together has the state has the state phi plus, right? Now setup. Now suppose Alice has a qubit or another qubit Q, and that particular qubit has the quantum information, has the quantum state or quantum information stored in the state secret psi, right? In the qubit, stored in the qubit Q, and that C wishes to transmit to Bob, right? So of course, Alice is unable to send this Q to Bob physically. C is only these are certain things. Okay, so I'm writing these things to avoid various even after the classes there may be various confusions that are you sending quantum informations? No, you'll be sending classical information. So Alice is, that's why I'm writing this part. Alice is unable to physically send Q or the information psi of Q to Bob. She can only send classical informations. So classical part of this psi in this teleportation protocol. She can only send the classical information, because um, classical information only you can transfer over fiber optics or whatever way, right? So that is you can do. She can Alice can do, right? Now the state, of course, the state Q is unknown to both Alice and Bob. What do I mean unknown? Unknown means if B knows information Q, then there is no point of communications, because so Bob should not know what Alice wishes to tell, right? That is sure. And unknown to Alice means Alice does not do measurement on this particular qubit Q, right? What will be the quantum state psi? It will be there. It will not do measurement directly, right? Third protocol is, I mean, the third setup protocol is the correlations between Q and other systems. Suppose other system is A, means Alice has the initial register A and C has another registers Q, and the correlations between Q and A must be preserved during transmission. It should not be lost during transmission. If there is a correlation, that should be intact. Third, and the last point is, by no cloning theorem, if Bob receives the transmitted information, right? Transmitted information psi, get psi, right? Then Alice must not have the qubit in original state, right? So this is the protocol setup, right? Yes. What is correlation? Okay, I'm skipping these questions. Maybe ChatGPT is better to answer. Okay. So correlations, independence, these are very basic properties of the random variables. Especially we have studied in the classical communications theory, right? And maybe this, yeah. So now, mm, so in fact, no question is funny, because any question has deeper meaning and it can have a better philosophy to answer, but I'm skipping this part. Okay. Okay. So now, here it can be entanglement as a correlation you can consider. Now, let's understand the circuit and the mathematics behind the circuit. Okay. Every time this is creating problem. So circuit part. So this is the register for Alice. Alice has the register A, and Bob has the register B, right? And they have the entangled pair 5 plus, um, and this um, there is another quantum register, that is Q, which has the information psi, and Alice wishes to transmit the state psi of qubit Q to Bob. So that is the objective, because part of the So downside is for Bob and upside is for Alice. So this is the part of the circuit, right? And we'll see this protocol. And so ma'am asked about the correlation, ma'am. And here the correlations you can simply create between the qubit Q, where the information is stored at psi, right? And there is a correlation between psi and A, right? That correlations that maybe there, it may not be there, right? You can have an entangled information. So, and this protocol is that first you do a C naught applications, that you make an entangled pair between Q and A, and then you apply the Hadamard here, and you do the quantum measurement here. So I'm not doing the direct measurement. After applying these entangled operations followed by the superpositions gate, Hadamard gate H, right? And why I'm applying this, I'll come back. So all these answers will be clear when we'll be doing the mathematics part. So then Bob applies X and Bob applies G operator, Pauli G operator. And theoretically, he should get the state psi that Alice wishes to transfer, right? And for that, I cannot communicate the quantum information. So I do the measurement and I transfer the classical data to Bob. So classical data is retained with two lines, and quantum data the transfer is written with the single line. So this is just a convention. Okay. So this is the circuit for this, and suppose this is a step 0. This is step 1, step 2, right? So there are mathematical steps, and we'll come back. So you can draw the circuit. I'll slowly scroll it up. Okay. And please, if you have, if any one of you or some of you are writing on A4 page, so one page you just draw this circuit and keep it side, and the continuing page you can just keep writing, right? Because this circuit will call every time when we'll be writing the math. Okay. And suppose after this measurement, this particular classical information is little b, and this classical information is suppose little a, right? Now, the teleportation protocol. So I'm just writing what we have done in just a brief way. So and together with the condition of operation. So first protocol is that Alice performs. So first of all, what are the quantum registers we have? We have Alice has the quantum register A, Bob has the quantum register B, and Alice has another quantum register, that is Q, right? So the initial state is QAB. These are the three registers, and Alice wishes to transfer the information Q that gets high or in qubit Q to the register B to Bob. Okay, so this is the objective. So now for that, first what it does, Alice performs a control not operation. Controlled not operation. That is what we call C not. Controlled not operation, where Q is the control qubit and A is the target qubit. Right. So this part. So this is the control qubit and this is the target qubit. This is the first step. Second, Alice performs a Hadamard operation on Q. So here on the control qubit. Third is, yeah, I am explaining the circuit, how it is working, exactly that protocol I'm writing. And we will, why we are using this circuit, and mathematics will come back. Why this is important. Then you can think something magical, right? There is no quantum communication channel, just classical information is transmitted, and still I am saying that okay, psi is here somewhere and you are getting somewhere else, right? How it is happening? Okay, so that is the magical part, but I will see this magic using simple mathematics. Okay, so just let me finish this protocol part. And Alice measures A and Q, obtaining binary outcomes A and B. So after applying this C naught and Hadamard, it does simple quantum measurement and gets the classical value A and B, which are binary, 0 and 1. Okay. So then Alice sends the classical information A and B to Bob by say fiber optics of certain things. Okay. Over classical channel, for example. Right. Now Bob performs for the following operations. The following operations. So Bob is only getting A and B, right? So Bob is doing, if A equals to 1, then Bob applies X operation, Pauli X, okay? X operation. Operations. Bob applies X gate. If A equals to 1, then gate, and if B equals to 1, if B equals to 1, then Bob applies G operations. Pauli G gate, okay? B operations to the qubit B, right? So in table form, if we write something like this, so the condition is what are the values A and B can take, because they are binary, right? They can be 0, 0, they can be 0, 1, they can be 1, 0, they can be 1, 1. These are the four possible possibilities, because the original informations was only the 0 and 1, right? The single qubit informations. So they can be classically either 0, 0, 0, 1, 1, 0, 1, 1. These are the four possibilities. So if A and B both are 0, so then Bob does nothing. That means it applies only identity gate. If you multiply any vector with identity matrix, then it will be the same identity matrix. That means it does nothing, right? If the B equals to 1, it applies G operations, G gate operations, right? This is basically identity matrix. matrix. Now, if A equals to 1, it applies X operations, Pauli X operations, right? Pauli X gate, this is Pauli Z gate, right? Pauli G. And if both are 1, it applies GX operation. So this is the philosophy, or this is the actions taken by B, right? Now, why B suddenly takes this action? Now, let's prove this mathematically. So please look at the circuit. So there are certain things I have written. That is step 0, step 1, step 2, and I'll come back. I mean, what is the quantum state here? What is the quantum state here? What is the quantum state here and here, and so on, right? We'll come back there. So suppose I have taken psi as alpha ket 0 plus beta ket 1, right? Suppose this is my state, right? And then what is the step 0? So A and B, they are sharing a joint entanglement, right? They have an EBIT share. They are sharing a EBIT, right? They are entangled pair, right? They are sharing one entangled bit of informations, and that's why they have the state phi plus, right? And you want to transmit with the qubit q. So that means jointly they have the state this one, and it has the state psi. So the joint representation is this tensor product with this. So we are going from the way we are reading the circuit from bottom to top. Okay, bottom to top. So this is the qubit number 1, 2, and 3 this way. Okay. So because we always represent information from receiver to transmitter, like we model y equals to hx, right? So this is we read first, then we read this one, then we read this one, right? This way classical communications also you model. Similarly, you read this as first, then this one, then this one. So this together has the state phi plus, and you have another state psi. So what is the joint state? Phi plus and psi, right? This is the joint state. And this is equals to 1 upon square root 2. What is phi state? That is 0, 0 plus 1, 1. 4 times alpha 0 plus beta 1, right? So this is the tensor product, and this is the psi part, and this is the entanglement part, right? The entangled state. So I call this as a pi 0 state. This particular state I call as a pi 0 state, which is just if you do multiplications of these two quantities, you'll be getting as alpha 0, 0, 0 plus alpha 1, 1, 0 plus beta 0, 0, 1 plus beta 1, 1, 1 by square root 2. Right? Now step 1. So step 1, we have applied C naught, right? C naught applied to Q register. This is what we have done, right? So then so we are reading the circuit from left to right, right? Sorry, from bottom to top. So bottom to top means this is my first qubit. This last one is my first qubit. This is the first qubit. How many qubits are there? There are 3 qubits. 1, 2, 3. That's why the digits are written in 3 this way, right? So this is the first qubit that I have Q0, Q1, Q2 this way. This belongs to the register B, this belongs to the register A, and this belongs to the register Q. Right? And together they are making the computational basis from 0, 0, 0 to 1, 1, 1. Right? This is the register setup in the circuit. Okay. And there is a question why phi? So because they are sharing they are saying their joint quantum state is a psi state, like the Bell state, right? For example. So then the representation is this, because there is a circuit between A and B, right? And or A and B has certain photons and they are entangled photons, for example, right? In reality, but in circuit, simply we have an entangled preparation circuit in the superconducting setup. Now, So pi 1 state. What did I tell yesterday? Even without doing any mathematics, because CNAT has a representation like this. So that is 0, 0 outer product with identity matrix plus 1, 1 outer product with Pauli X matrix. This is the definition of CNOT. This is a unitary matrix of 4 cross 4 dimension. So if you multiply this matrix with this, it is a means you have to write a lot of equations. But there is a philosophy. You don't need to write math. The philosophy is if the first qubit is 1, the second qubit flips, right? That way, if you write, so the first two quantum state, if you see 0, 0, 0 means the first qubit is 0, so it will do nothing here. So the state will be alpha 0, 0, 0 will be intact. Then alpha 1, 1, 0 will be intact. Third is this one, where the first qubit is 1. So the state will be beta 0, 1, 0. Sorry, 0, 1, 1. Right? This will be my state. So just let me take 0, 1, 1. This will be my state. And the last one will be beta 1, 0, 1. So because the first qubit is 1 means the second qubit will flip, right? Here also second qubit will flip. So this is the state at step number 1. Till this, I think it's okay, right? So you please see the math. I'm just coming back in 1 minute. You can take a break of 1 minute and I'll come back. Sorry. Um, so so in the circuit, you can see when you are applying C naught and when you are applying now we'll start the Hadamard part. But this is your first qubit, right? This is your first qubit, this is your second qubit, and this is your third qubit, right? So that is BAQ is the configurations Q0, Q1, and Q2. So when you see this as equals to 1, then this qubit will flip, right? If and accordingly, that is the purpose of this C0 gate, right? C0 apply is not clear. Okay, so what was my pi 0 state? Just let me write the pi 0 state again. Pi 0 state was 0, 0, 0 plus alpha 1, 1, 0 plus beta 0, 0, 1 plus beta 1, 1, 1. This was my state. This state should not have any difficulty, right? This is just a tensor product of the entangled bit and your the quantum state psi, that is alpha ket 0 and beta ket 1. Just I have done simple mathematical multiplication 0, 0 and 0. That means alpha 0, 0, 0. Just simple arithmetic multiplications, right? Cartesian multiplication, simple. Now, when you apply the C naught gate, how you are reading the qubit? From right to left. Okay, if you just multiply this is entirely as a vector, right? And you are applying the C naught gate, that means C naught times this pi 0 state, that will be your pi 1 state, right? You can do by hand with this times this one, you can do by hand. But I'm telling you the answer you can also find out using this philosophy, that just look at the first qubit, where it is 1. So only here and here you can see 1. If the first qubit is 1, the second qubit will flip. This and this will flip. So now look at this state, pi 1. So these are 0 zeros, means if it is 0, it does nothing to the other qubit. So that means 0 0, this state and this state will become same. Here the beta is 0 0 0 1 state will become 0 1 1, because 1 will be 1 and the second qubit will be flipped from 0 to 1. Here also the second qubit flipped from 1 to 0, right? Rest as same. So I hope it makes clear, right? So this is just by philosophy, just by you can do by like it's a shortcut, right? Otherwise you can simply do the math and you will reach here again. Okay. Now step number 2, we applied the Hadamard, right? We applied the Hadamard. I'm very sorry, I'm taking some more time in Sunday, on Sunday, so I'm very sorry. So thank you for your patience. So when you apply the Hadamard, what Hadamard does, you applied Hadamard, and Hadamard does that your 0 will become plus state and 1 will become minus state, right? This is the purpose it does, right? So now pi 2 state will be, so I have alpha 0 0, and last this particular 0 will become plus state, plus alpha 1 1 plus state, plus beta 0 1. So you look at this particular configuration, right? Beta 0 1, the last bit is 1, so minus state, right? Plus beta 1 0, and this 1 will become the minus state, right? And so if you write this way, and if you expand, in fact 0 equals to this plus equals to ket 0 plus ket 1 by square root 2, and this equals to ket 0 minus ket 1 by square root 2, this way, right? This is the expanded form of plus and minus. So apply that and you will be getting alpha 0 0 0 plus alpha 0 0 1. Just we need to keep some patience. In the age of AI, we lost our patience. So even just there is a step, I have done one step jump here. So just I have put the values of plus and minus and rearranged it, right? So then alpha 1 1 0 plus alpha 1 1 1. So these are all the alpha states, plus beta 0 1 0 minus beta 0 1 1 plus beta 1 0 0 minus beta 1 0 1. Entire quantity divided by 2. Why it is 2? Because uh, so I forgot to write this pi 0. It has some square root 2 term, right? Pi 1 will also have something, the entire quantity by square root 2, right? And this pi 2 state will have a square root 2 times this square root 2. So square root 2 earlier and the square root 2 in plus this square root 2 times square root 2 will become 2. Okay. And in general, there is an intelligent way of writing it as half of alpha ket 0 plus beta ket 1 0 0. If you look this entire equation which is derived from here, then you put last to 0 in this way. So because this product is ultimately 0 0 0, so this way. So alpha ket 0, and somewhere where there is another 0 0 for beta, like here. So this particular term, if you look at, right, this particular term, if you look at this term and this term together, you can write this way. So alpha ket 0 plus beta ket 1 0 0. Similarly, by arranging all the terms, you can write in this way: alpha ket 0 minus beta ket 1 0 1 plus half of alpha ket 1 plus beta ket 0 1 0 plus half of alpha ket 1 minus beta ket 0. Just arranging, I am arranging it. Why I am arranging this way? Because my informations, I am just writing the classical way of understanding is 0 0 0 1 1 0 and 1 1 in this format, right? If you can write in this format, then and you are trying to understand, okay, um, this is the way, this is because your right hand side was the ket size state, right? And the first part was the phi state initially, right? This was your initial state, and you are writing this right side part as this 0 0 0 1 1 0 and 1 1. As such, these are the outcome A and B, right? So that means the probability of A equals to 0 0 equals to 1 4. If you do the measurement in the basis 0 0, in the basis 0 1 1 0 and 1 1, each case you will see the probability is A 0 1, uh, probability of A equals to 1 0, and probability of A equals to 1 1. Each case you will see the probability 1 4 1 fourth 1 fourth and 1 fourth. This is the probability of each individual state, right? Now let's do one table and things will be easier then. This is AB. This is the probability. Then the conditional state. Conditional state is B, A, Q from last to first, right? Bottom to top. Then operation by B. Operation by B. And the final state. So what are the classical information may have? It can be 0 0, it can be 0 1, it can be 1 0, it can be 1 1. These are the four possibilities, and all the possibilities has equal probability: 1 fourth, 1 fourth, 1 fourth, 1 fourth, that we have seen. So all the probabilities are 1 by 4, right? Now that is fine, but what is interesting is that for the state 0 0, what is my conditional state? Conditional state is alpha ket 0 plus beta ket 1 0 0. This is my the quantum state vector, right? Then alpha 0 minus beta 1 um, 0 1. Then alpha 1 plus beta 0 1 0. Then alpha 1 minus beta 0 1 1. So just this step, I'm just writing this step, same step in this table form, right? Now operations, what it does, if this is the outcome that A and B are 0 0, right? Then B has to do nothing. It just does identity operations, right? Identity matrix multiplication, because B already received the state psi, because psi is equals to alpha this alpha ket 0 plus beta ket 1. You look at this. This is the register B. This is the register B, because my format is what? My format is B A Q. This is my first quantum register. This is my second. Sorry. This is my first quantum register. This is my second quantum register, and this is my third quantum register. Like the circuit I have drawn from bottom to top. If you see Q0, Q1, Q2, right? And I have written the equation in such a format that B is this one. So this particular information, this is the information stored in the register, right? So if A and B in the classical communication system, that is, if you see the circuit part again, if this is equals to 0, if this is equals to 0, that means B has to do nothing because B already stored psi, right? Then if B equals to 1, right? If B equals to 1, classical information B equals to 1 and A equals to 0, right? So the corresponding state is alpha ket 0 and beta ket 1, 0, 1, right? Now B applies, if B equals to 1, then B applies this, Bob applies G operator, right? What is the purpose of G operator? Yesterday we already studied it. If the qubit is 0, it does nothing because G applies on 0, gets 0. G applies on 1, gets minus of this ket 1, right? So if you apply G operator here, alpha ket 0 will be alpha ket 0, but beta ket 1 will become plus beta ket 1, right? That means you get alpha ket 0 plus beta ket 1 just by applying the G operator here. If you apply the G matrix in front of the state vector here, right? So if you apply here, so alpha ket 0 will be alpha ket 0 because this particular property, eigenvalue property, right? You can apply and you will be getting alpha ket 0, beta ket 1. This phase flip will be happening, right? Just by using the G operator, right? Phase change, right? Now similarly, if you apply here in this particular case, if you get the classical information as 1 in the classical, from the classical channel you receive A equals to 1 and B equals to 0, then your state is alpha 1 and beta 1. So that means if you look at the original information, there is a bit flip, right? So if you apply X gate here, so this 1 will become 0, this 1 will become 0, and this 0 will become 1. So that means alpha 0 plus beta 1. And if you have this particular configuration that A and B both are 1, classical information is both are 1, then there is both bit flip and phase flip. So you apply the GX operations. So then it will become again alpha 0 plus beta ket 1. So by doing all these mathematical operations, each time you are getting the state ket psi. That means you transfer the informations from this quantum registers Q from the quantum register. So Q to so you can transfer the informations from Q to the Q to B. So at least transfer the informations from the registers Q to B. The information transfers as psi by doing this circuitry. So this is the theory part for the quantum teleportation part. So if you have any questions, please feel free to ask me. And then I will run the Qiskit program, right? So I'm giving 1-2 minutes. So if you have any question, you can put it in chat. So let me get the so you can open your laptop. I'll slowly start the um, programming part. So let me just get the setup ready. Yes, yes. So the for 8-bit also you can follow the step. The mathematical equation will slightly change, but the protocol will be fairly same, right? The circuit protocol will be same. Only the equations will be bit different. So just teleport. Installation already Devanshu also written, and I have given entirely in the chat. Please look at the chat. I mean, how to install Python package there are lots of YouTube videos you can see. Like you can download either Anaconda, so in Anaconda or any Jupyter notebook or Colab, or in fact the VS Code that I'll be using. Right, these are various environment to write code. I mean, it's very difficult to show from online lecture, right? If I mean, in general, I understand the difficulty. In general, if it is a lab class, it is easy, but otherwise, it's very difficult. So just screen. Um, I just closed my writing pad and I am opening it from. Let me open the chat also. Just allow me a couple of minutes. Just getting my setup ready, because otherwise I cannot take your questions. Chat, yes, got the chat box. Yeah, so I'm very sorry because I understand that some of you may have issue to install, especially the senior faculty members. And I have shared all the guidelines, the Qiskit guidelines, so you may follow that. That is one way. Okay, so is the screen visible? Can someone confirm? Is this?
Yes, the screen is visible.
Thank you.
And I request all the participants who have not installed till now, then they can watch from the YouTube also. It is
Yeah,
also recorded on the YouTube lecture. So first concentrate on what sir is saying and understand that how it can be done. And after that, for practice, you can go for the YouTube and see this lecture online. Thank you.
yeah, thank you. I mean, the hands-on online is often a problem. So sorry for
It
that.
is actually the participants
Yeah,
who are not familiar with these
yeah,
platforms, then they will
I
get
understand,
trouble with
sir.
this.
Especially the senior faculty members may face difficulty.
Hmm.
Yeah,
Yes.
so this is just how we write the hello world in Python, right? And for the teleportation circuit, so let's do the teleportation part. Quantum teleportation. So those, I mean, who are facing challenge, please just watch these things, and maybe later, if we get a chance, we'll again repeat this thing. Okay. So I need to call the Qiskit library. So import Qiskit instead of specific library. I am just calling uh, just from Qiskit. From Qiskit, I am importing everything. Okay, so for everything, just put star, right? So import star means anything I can take help from the library Qiskit. Okay, so from Qiskit, import everything. Now, Suppose let's take how many registers in this experiments are required? 3 registers, right? So QC equals to quantum circuit 3 comma 3, 3 quantum register, 3 classical registers. Suppose we take 2 is fine, 2 classical registers are also fine, but I'm taking 3 just for simplicity. And suppose you do QC dot draw. So you can see just I have designed a quantum circuit just by calling quantum circuit, and this quantum circuit functions is defined in the library Qiskit. Okay, so QC is quantum circuit 3 comma 3 means it has 3 quantum registers, quantum registers, and the registers are B, Bob, Alice, and Q. Right, the Q in has the informations psi. Right, and we haven't defined anything else. Now, in the teleportation circuit, we have seen that suppose first let's create the entangled pair between the Alice and Bob, right? So to do that, let's do QC dot X in the first register, and let's do QC dot draw. Those who wants to see the colorful picture, so they can use this MPL function. QC dot draw is the draw functions for the circuit, and MPL is taken to see the color plot. Here we haven't see the color plot. For example, QC dot draw without anything. And if you write the MPL, you will see the colored versions like this. The quantum resistor is 0, quantum resistor 1 and 2. And you applied suppose your quantum state is X, right? X means poly X, right? So your quantum state is poly X times Q0 is the quantum state you want to transfer. That is your psi state, right? That you want to transfer. And for a clear visualizations, often we use the something called the barrier, right? So often we use these things as barrier thing like this. So it does nothing. This barrier, that QC dot barrier and MPL is you are just I was doing the step 0, step 1. This kind of mathematical simplifications. For simplifications we use this barrier, but it has no purpose in the circuit. It does no mathematical operations on the circuit. Okay, this is just for visualizations purpose. So QC dot barrier. So those who are missing, I'm writing the code here also in the chat box. Chat box, you can copy and paste maybe. So let me copy and paste the code here. And we have taken our quantum state as just this x0. X0 means the initial state was psi state, right? Here psi state equals to x times get0. Right. This is how we define the psi state, right? That's a very simple one. Now, as per circuit, we have to apply a now suppose I apply a Hadamard in first register, that means Q1, and then I apply a CX between 1 and 2 qubit, right? Control C naught. So what it does, so I created an entangled pair between Q1 and Q2. This is the Bell state circuit, right? Between Q1 and Q2. That means I created an one E bit between Q1 and Q2. Hadamard followed by a C naught. So I have written that QC dot H1, that means the first register. So Python start counting from 0. 1 mean this particular register, right? The second one. And between 1 and 2 means Q1 and Q2, I have applied the C naught, right? That's how I prepared the entangled informations between Alice and Bob, Q1 and Q2 register, right? Now my setup is ready, right? My setup is ready means I have an entangled bit between Q1 and Q2, Alice and Bob. Now Alice has additional qubit, that is Q0 here, and that has certain informations, and that information is 0 times kx. That means it has information kt1. Kt1 is the information that Alice wished to transfer from the circuit Q0 to Q2. Q0 to Q2. Okay, that is the purpose of the teleportation circuit. Instead of X, you can define any arbitrary quantum state K psi. This is a very simple demonstration I'm giving, but eventually you can take any other instead of X, you can take any other state K psi. Okay. So now, as per the circuit, what we have to do? As per the teleportation framework, first we have to apply the C naught between the Q0 and Q1. So that is Q0, Q1 means the, in theory, it was the register Q and it was the register A. Q1 was A, right? Between Q0 and Q1, we have applied the C naught, and then we applied the Hadamard in the qubit Q, right? That is Q0. So now let's do another barrier and do the measurement. So what we have done, if you see in the theory, there is a measurement in the qubit Q, and there is the measurement in the Alice qubit A, that is Q1 here. So these are the two measurement, and they can have value, say 0, 0, 0, 1, 1, 0, 1, 1. These are the four possible values here, right? Now accordingly, B will take decision. So I'm taking another barrier here, and QC, it applies Cx between 1 and 2. QC dot Cz between so you are measuring the Q0 and Q1 qubit. Okay. So this 0, 1, just forget whatever it is, just forget. This is just coming from the computer. Some garbage value will come. What are the things will be seeing? We should not look at this value. Okay. So B, the register B will see this value, whatever these are the values, and accordingly, this register Q2 will apply the logic. Okay. Cz. Okay, now you can see what are the things I have done. In theory, I have said that you have to apply an X gate, right? And you have to apply a Z gate accordingly, right? But these two gates can be applied in quantum circuit as a controlled operations, in fact, because that will make sense. Otherwise, you have to take another auxiliary qubit to state prepare. So these are simply, instead of X and Z, you are using Cx and Cz between 1 and 2 and between 0 and 2. This is just another twist, another level of twist in the actual circuit. So control X and control Z you are using. Then from Qiskit, we are using this visualizations plot is required, and we will transpile this circuit, and we'll see. I mean, we have the circuit, but now we have to execute this circuit, right? So for that, we have a function in Qiskit called transpilation, which will map the this kind of logical circuit to the physical actual hardware mapping, the qubit mapping, and also it will check if it can optimize the number of gates and all. So that particular function in Qiskit is called the transpilation function, so the transpile function. So the actual circuit QC I have stored in the variable name circuit, and then I called a simulator. You can take if you have hardware access, you can use the hardware also backend as a hardware. But here we are using the simple quantum simulator. So AR simulator we have used. So AR simulator we called from Qiskit AR. Okay, and then some of you may, after installation, you can see that Qiskit AR is not running. So they have to install Qiskit AR separately. So for that, the command is pip install Qiskit AR. You can install. So those who are using Qiskit versions less than 1, so this was there, but in Qiskit 2.2 and Qiskit 2 onwards, this is actually removed from actual Qiskit package. So you have to install this Qiskit if you want to use the AR simulator specifically. And after this transpilation of the circuit, you are running for 1,000 times. And you will see how many times one particular quantum states is repeated. And you are taking the histogram plot. So let me give the code for this part. This part and this part. Now, if I run this thing, you can see that we have the states 100, 101, 110, and 111, right? So these are the 4 possible states I am getting. That means 00, 01, 10, and 11, right? So and because 00, 01, 10, and 11, these are the 4 combinations of the classical bits, right? A and B that we have seen in the theory. But every time you see the first qubit, that this first qubit means the register in B, Bob, right? Every time it is 1, 1, 1, and 1. Why every time it is 1? And so theoretically, we have seen all the 4 probable state has the probability same, right? Now, earlier I was saying this should be psi 00, psi 01, psi 10, and psi 11. But initially, what was my information? My information was I started initialize the circuit Q0 as Ket0. Any qubit you initialize with 0, and you applied the Pauli X gate. So if you apply the Pauli X gate, that means the informations become Ket 1, 0 become 1. And this is the information you wish to transfer from qubit 0 to qubit 2. That's why every time you see this is the first point is 1, 1, 1, and 1. That is what you received at the receiver, right? So this is the quantum teleportation circuit, and you don't see all are exactly this, right? So that's what actual reality in probability you won't get the 1/4, 1/4, 1/4, but close to 1/4, right? Even when you will run it on the hardware, so this value will abruptly changing based on the noise property of the hardware, right? So or the noise behavior of the qubit and the gate operations. So this is the demonstration of the quantum teleportation circuit. And with this, I'm closing this session. I'll be sharing the notebook also. Don't you need not worry. And let me know if you have any further questions.
Thank you very much, sir.
Sorry, I took a bit more time today. About 40 minutes I took extra. I thought to
It's
show
okay.
some demo because participants may get interest. Yeah.
Sure. So there is one question which has been posted.
Yeah. So if you run the simulator for another 1,000 times, the values might differ. Yes. So actual experiments that is what the superposition theorems tells us, right? That out of the 4 possible states, 0, 0, 0, 1, 1, I mean here actually 8 possible states, right? Because you have 3 quantum registers, but your circuitry is giving 4 out of them from the mathematical derivations. We have seen 4 terms are there, right? And in that 4 terms, the combinations are 0, 0, 0, 1, 1, 0, 1, 1. And how many times you repeat and how many times they are basically occurring depending on them. These values will be roughly closer to 1/4 probability, but not exact 1/4 from the practical result. how to see that information is transmitted. Okay, so that's how to see that information is transported. So in circuitry, you need to look at the states that you are getting from the histogram, and the first qubit of the histogram, you can see that how it is like. So if you are representing your information in multi-qubit state, for example, the Q register, so then you will, instead of 3 qubit, you will see 4 qubit or 5 qubit representation. And depending on the last 2 qubits, if you see, okay, all are the same, that means teleportation is complete. And in the initial qubits, that is the Bob register qubit, depending on that, you can check if they are same, then that is the information that is transmitted from the register Q. Any reason you move to VS Code from Jupyter Lab? VS Code we use in industry. Okay, this is very flexible for writing code in.
There is one more question before that. If you probably how to see that information is transported, you have already answered.
Yeah, I just answered that one. And any reason you move to VS Code? VS Code is is a multi is an interface to code any programming language, C, Python, Rust. So we often use various programming language for various industry works. So this is very comfortable one. Otherwise, Jupyter is good for Python. Can you design this using MATLAB? I don't know whether MATLAB has some extensions like that or not, but Qiskit does. So please use Qiskit. Is our IBM product, and this is globally people use it for research and development. Qiskit is just, you can simply pip install Qiskit. I knew it, but this is possible to design same circuit using MATLAB code. I knew it, but is it possible to design same circuit using? I don't know. MATLAB should have some extension like that, but MATLAB does not provide simulator or hardware. Okay, so you can use instead like simulator like Penny instead of like, if you are comfortable with Qiskit, that's great. The other alternatives are Penny and Google Sark, etc. Advanced happy Pongal everyone. Thanks. Weak coherence versus entangle-based QKD. Okay, you may ask these questions to professors in the who will be delivering the QKD sessions. They will be, I mean, they are expert in that field. For quantum teleportation, not sure. I don't have a good answer for that. Qiskit is Python library. Yes. Thank you. Yeah, I think I have covered most of the questions, sir.
All right. Thank you, Rahman, for accepting our invite and giving these four informative sessions related to quantum communication, quantum information theory.
Thank you, sir.
And I hope participants have also enjoyed the practical session which you have demonstrated using Qiskit. Thank you very much, and we hope to see you again in future FD.
Sure, sir.
Thank you. Thank you very much.
Thank you so
Thank
much.
you for your time.
Yeah. Thank you,
So,
everyone. Happy Pongal. Thank you. Yes, sir. Yeah.
yes. So, I mean, I was just announcing some things related to participants. So, basically, the next session we will be having on 15th after Pongal. Pongal and happy Makar Sankranti to all the participants. We will be meeting again on 15th, same time, 3 to 5 p.m. All right. Thank you all. So, we are. Thank you very much.
The quiz, regarding quiz, there is also an announcement. The quiz starts at 6 p.m. from today, and it is open till 14th night. So all participants are requested to attempt the quiz.
Yes, the quiz are simple. You can just, I mean, you can refer the notes. We'll not be putting questions related to the sessions held by Dr. Rahman. The quiz is really been covered before this. So Dr. Rahman's questions would be put into the quiz number 2. Thank you.
Yeah. Thank you so much.